Welcome to this lecture on the evolution of parasitism. Today, we are going to explore one of the most fascinating journeys in biology. We will discover how independent, free-living organisms completely transformed their lifestyles to rely entirely on other living beings. By the end of this session, you will understand not just the biology, but the mathematics behind how parasites evolve, adapt, and survive. To begin our journey, imagine a burglar who realizes that instead of breaking into houses every night, it is much easier to just move into someone's basement, eat their food, and hide. Over many generations, the descendants of this burglar might forget how to survive outside, but they become absolute experts at staying invisible inside the house. In the natural world, this is exactly how many free-living organisms transitioned into a parasitic lifestyle. Instead of hunting for food or braving the harsh environment, they found a way to live on or inside another organism, getting a free ride and a constant food supply. Now that we understand what parasitism is, let us look at how it changes the organism physically. This evolutionary pathway involves a series of genetic and morphological changes over millions of years. Parasites often undergo regressive evolution. This means they lose complex organs like eyes or digestive tracts because the host provides everything they need. Simultaneously, they develop highly specialized structures, such as hooks, suckers, or complex reproductive systems. These structures ensure they can attach firmly to the host and spread their offspring efficiently. It is a directional shift driven entirely by natural selection. This fascinating biological shift leads us to ask why we need to study it. Understanding how parasitism evolves is absolutely crucial for modern medicine, agriculture, and ecology. By studying this evolutionary process, scientists can predict how parasites might adapt to new drugs. This helps us stay one step ahead of drug-resistant diseases like malaria. It also explains why certain parasites only infect specific hosts, which is vital information when trying to prevent animal diseases from jumping to humans. Without this knowledge, we would be completely blind when developing vaccines or designing pest control strategies. Understanding why we study this brings us to the question of how we measure their success. To truly understand how a parasitic trait evolves, we must look at how successful a parasite is at spreading. In evolutionary biology, a parasite's fitness is often measured by its basic reproduction number. This number tells us how many new infections a single parasite will cause in a completely susceptible population. If a genetic mutation increases this number, that mutation will be favored by evolution. It will then spread rapidly throughout the entire host population. To measure this fitness mathematically, we use a fundamental equation. The basic reproduction number, called R0, equals the transmission rate beta times the population density n, all divided by the sum of the natural death rate d, the virulence alpha, and the recovery rate gamma. Conceptually, the numerator represents how fast new infections are created, while the denominator represents how fast infections end. If the transmission rate increases, the overall fitness increases, meaning the parasite is more successful. Conversely, if the virulence becomes too high, it kills the host too quickly. This increases the denominator and actually decreases the parasite's evolutionary success. Before we move on, let us see this formula in action with a concrete example. Imagine a population of 500 wild rabbits infected by a parasitic mite. A new mutation creates a strain with a transmission rate of 0.02 per day. The natural death rate is 0.01, the virulence is 0.04, and the recovery rate is 0.05. We multiply the transmission rate by the population to get 10 new infections per day. We then divide this by the sum of the ending rates, which is 0.10. The result is an R0 of 100. This means the strain will successfully spread.
This successful spread brings us to an important evolutionary concept known as the trade-off hypothesis. Parasites cannot simply increase their transmission rate without consequences. They must carefully balance transmission and virulence. If a parasite replicates too aggressively to spread faster, it often causes more damage to the host. This means the host might die before the parasite has a chance to jump to a new host. Therefore, natural selection forces parasites to continuously fine-tune their traits. They must balance how quickly they multiply with how long they keep their host alive to maximize their reproductive success. Let us test this hypothesis by calculating a new scenario. Suppose the parasite evolves a new trait that doubles its transmission rate to 0.04 per day. However, this aggressive replication also increases its virulence to 0.14 per day. The host population, natural death rate, and recovery rate remain the same. We update our numerator, which now gives us 20 potential new infections per day. But our denominator also increases to 0.20, meaning the infection only lasts 5 days instead of 10. Dividing 20 by 0.20 gives us an R0 of 100. Now that we have calculated both scenarios, let us formally prove why this happens. We are setting up a mathematical comparison to see if the new aggressive trait provides an evolutionary advantage. We defined the initial fitness as R1, which we calculated to be 100, with an average infection duration of 10 days. We defined the mutant fitness as R2, which is also 100, but with a shorter infection duration of 5 days. For natural selection to favor the new mutant strain, the value of R2 must be strictly greater than R1. This is the core requirement for evolutionary advancement. Continuing our proof, we look at the final comparison between the two states. When we compare R1 and R2, we see that 100 is exactly equal to 100. Because the fitness did not increase, the aggressive mutation yields no net increase in secondary infections. Even though the parasite evolved to transmit twice as fast, it kills its host so quickly that it has exactly half the time to spread. Therefore, we have proven that this specific aggressive trait does not provide an evolutionary advantage over the older strain, perfectly illustrating the trade-off hypothesis. This mathematical proof is perfectly visualized in the following graph. What you are looking at is the evolutionary trade-off curve. The horizontal axis represents the virulence, or host mortality rate, while the vertical axis represents the transmission rate. Notice how the solid curve rises steeply at first, but then begins to level off. This shape shows diminishing returns. The distinct point labeled on the curve represents the optimal evolutionary fitness, where the basic reproduction number is at its absolute maximum. It visually demonstrates that infinite transmission is impossible without killing the host too fast. As we conclude our lecture, let us review the most important ideas. First, the evolution of parasitism is a directional shift where free-living organisms adapt to rely entirely on a host, often losing complex organs in the process. Second, evolutionary fitness is measured by the basic reproduction number, which dictates whether a new trait will spread. Finally, the trade-off hypothesis shows that parasites are locked in an evolutionary arms race, constantly balancing transmission rates against host mortality to ensure their own survival. You now have a solid understanding of the evolution of parasitism.